The universe is 13.8 billion years old, but the edge of what we can see sits 46 billion light years away. That number doesn't add up. If light has only had 13.8 billion years to travel, how are we seeing things that far? And more unsettling, the universe we can observe might not even be 3% of what actually exists. Every star galaxy, collision, explosion ever recorded only 3%. To understand what the observable universe really is, subscribe to support us. Now let's get into it. Most people assume that when scientists say the universe, they mean everything. All of it. The full expanse of space and matter stretching in every direction without limit. But that's not what astronomers are actually measuring when they point their instruments at the sky. What they're measuring, every photograph, every data point, every discovery in the last 100 years has been drawn from, is something considerably smaller and considerably stranger. It's called the observable universe. And the word observable is carrying a lot of weight in that phrase. It doesn't mean what technology can currently detect. It doesn't mean what a more powerful future telescope might one day reach. The observable universe is defined by something no machine can overcome: the speed of light and the age of time itself. Light travels at roughly 300,000 kilometers per second, fast enough to circle the entire Earth 7 times in a single second. But even at that speed, light takes time, and the universe has only existed for 13.8 billion years. That means there is a hard physical ceiling on how far any signal, any photon, any piece of information could have possibly traveled to reach us by now. Everything inside that ceiling is the observable universe. Everything outside it is simply unreachable, not because it doesn't exist, but because its light hasn't arrived yet. The boundary itself has no wall, no edge you could touch, no difference in the space around it. If you were somehow transported to the very limit of the observable universe and looked back toward Earth, you would not see a barrier. You would see open space continuing in every direction, with its own horizon extending 46 billion light years further in every direction. The boundary is not a place. It's a relationship between distance and time, a horizon that exists only from a particular vantage point. Think of standing on a ship in the middle of the ocean. You can see roughly 20 kilometers in every direction before the curvature of Earth drops the water below your line of sight. The ocean doesn't stop there. It continues. The horizon is not a wall, it is the limit of your geometry. The observable universe works the same way, except the geometry is not the curvature of a planet. It is the intersection of the speed of light and the age of the cosmos. And here is something that usually gets overlooked. Every single location in the universe has its own observable universe. A civilization in a galaxy 10 billion light years from here is standing at the center of its own bubble. A bubble containing billions of galaxies we will never observe, and excluding billions of galaxies perfectly visible from our position. Their sky and our sky overlap in some places. In others, they are looking at regions of existence permanently invisible to us, and we to them. There is no master view, no privileged position from which everything is simultaneously visible. Every observer is surrounded by their own private sphere of accessible reality, and beyond that sphere, the universe continues unseen, uncounted, unknown. The observable universe spans roughly 93 billion light years from one side to the other. One light year alone is about 9.5 trillion kilometers. To cross the observable universe at the speed of a commercial airplane would take approximately 80 trillion years, nearly 6,000 times the current age of the universe. At the speed of light itself, the crossing would still take 93 billion years. That is the space we can see, and it represents by most estimates around 3% of what actually exists. Inside that 3%, an estimated 2 trillion galaxies. The Milky Way alone contains somewhere between 100 billion and 400 billion stars. If you counted 1 star per second without stopping day and night, counting just the Milky Way would take more than 3,000 years. And the Milky Way is one of 2 trillion. The total number of stars in the observable universe exceeds the total number of grains of sand on every beach and ocean floor on Earth combined. And 90% of those 2 trillion galaxies are currently too faint and too far for any instrument we have to detect. They exist within our observable universe. Their light has technically arrived, but the expansion of space has stretched and dimmed it until it falls below the threshold of any current instrument. The James Webb Space Telescope, the most powerful observatory ever launched, is only now beginning to pull some of those galaxies out of the dark. What we can observe is already incomprehensibly large. What we cannot observe even within the defined boundaries is larger still. But none of that explains why the boundary sits at 46 billion light-years when the universe is only 13.8 billion years old. That gap is not a rounding error. It is the signature of something the universe has been doing continuously in every direction since the moment it began, something that makes ordinary arithmetic irrelevant when applied to the largest scales of space. Before moving forward, there is one more thing worth sitting with about the size of the observable universe itself. Not to impress with numbers, but because the numbers reveal something that doesn't register until you hold them for a moment. 93 billion light-years across. Inside it, 2 trillion galaxies. The Milky Way, as a representative sample of a typical galaxy, contains somewhere between 100 billion and 400 billion stars. Now try to place any of that in human terms. The Earth is about 12,700 kilometers in diameter. The Sun is about 109 Earths wide. The solar system, from the Sun to the outer edge of Neptune's orbit, spans about 60 astronomical units, 60 times the Earth-Sun distance. The distance to the nearest star beyond the Sun, Proxima Centauri, is about 266,000 times that 4.2 light-years. The Milky Way is about 24,000 Proxima Centauri distances across. Andromeda is 600,000 times the Milky Way's diameter away, and the observable universe contains 2 trillion objects, approximately the size of the Milky Way. At every step, the scale multiplies by a number that erases all the steps before it. The observable universe is not just large. It is large in a way that accumulates each layer of scale, making the previous one negligible. Earth disappears into the solar system. The solar system disappears into the distance to the nearest star. The nearest star disappears into the Milky Way. The Milky Way disappears into the observable universe. At the end of this sequence, the planet you are standing on is not just small, it is invisible against the full picture, not by degree, but by many orders of magnitude. And yet, the light from every step in that sequence, from the Moon 1.3 seconds away from Proxima Centauri, 4.2 years away from Andromeda, 2.5 million years away from the faintest galaxies, 13 billion years away, is all arriving simultaneously. Right now, every photon from every distance stacking up in a continuous stream from every direction. The observable universe delivers itself continuously in real time. Before explaining why the universe appears larger than its age, allows it helps to sit with what that age means in practice. Because the observable universe isn't just a spatial object, it's a temporal one. Every point in the sky corresponds to a point in time. The further away something is, the older the light reaching you, which means you are not seeing the universe as it currently exists anywhere. You are seeing a layered series of snapshots from different moments in history, all arriving simultaneously, stacked in every direction you look. The Moon sits about 380,000 kilometers away. Light from the Moon takes 1.3 seconds to reach Earth. When you look at the Moon, you see it as it was 1.3 seconds ago. Technically, the past barely noticeable, but real. The Sun is 150 million kilometers away, and its light takes 8 minutes and 20 seconds to arrive. A solar flare photographed this morning happened 8 minutes before anyone saw it. During the Apollo missions, astronauts on the lunar surface experienced a 2.6-second delay in every radio exchange, the round trip of signals traveling at the speed of light to the Moon and back. Even on what humans consider a local scale, the lag was already detectable. The Voyager 1 probe, launched in 1977, crossed the boundary of the solar system into interstellar space in 2012, traveling further from Earth than any human-made object in history. By early 2026, it was roughly 24 billion kilometers away. At the speed of light, a signal from Voyager 1 takes about 22 hours to arrive. Engineers at the Jet Propulsion Laboratory sent commands and waited almost an entire day to know whether the probe had received and executed them. Voyager 1 is not in another star system. It is barely outside the solar system, within the same star system that contains Earth, and the signal delay is already most of a day. Extrapolate from there. The nearest star, Proxima Centauri, 4.2 light-years away, would require a round-trip communication time of 8.4 years. A message sent to a civilization there would take 4 years to arrive. The response would take 4 more years to reach us. A single exchange would span nearly a decade. A conversation would require patience measured in lifetimes. A conversation with a civilization at the center of the Milky Way, 26,000 light-years away, would have a round-trip time of 52,000 years longer than recorded human history many times over. Proxima Centauri, the nearest star beyond the Sun, sits 4.2 light-years away. The light arriving from it now left more than 4 years ago. Sirius, the brightest star in the night sky, is 8.6 light-years away. The light you see from it tonight started traveling during a year that already passed in your lifetime. The North Star Polaris sits 430 light-years away. The light currently arriving from Polaris left that star around 1590, a decade before Galileo first pointed a telescope at the sky. No one alive has ever seen Polaris as it currently is. The nearest large galaxy, visible to the naked eye, Andromeda, sits 2.5 million light-years away. The light arriving from it now departed before anatomically modern humans existed, before cave paintings, before fire, before language, as we understand it. Our earliest ancestors were making stone tools on the African continent when that light began its journey toward us. If Andromeda were to disappear entirely tonight, we would not know for 2.5 million years. Every observation is a time machine. Every telescope is pointed backward, and the deeper you look, the older the universe you see. The Hubble Space Telescope demonstrated this in one of its most famous observations. Aimed at a patch of sky roughly 1/13 the diameter of the full moon, an area of sky that would be covered by a grain of sand held at arm's length and exposed for approximately 11 cumulative days, Hubble captured what's known as the ultra-deep field, a single image containing roughly 10,000 galaxies. Every bright point, every smear of light, every faint streak is a separate galaxy, an island of hundreds of billions of stars. The most distant objects visible in that image show the universe as it was more than 13 billion years ago, when it had existed for less than a billion years. The ultra-deep field is not a photograph of distant space. It is a cross-section of time, from the relatively recent past to the edge of the observable universe, compressed into a single frame. Then, James Webb launched, and the records started falling. In January of 2024, astronomers confirmed a galaxy designated JWST GS-Z140, seen as it existed just 290 million years after the Big Bang. The universe at that moment was roughly 2% of its current age. What Webb revealed was not what anyone expected: a galaxy already large, already bright, already containing substantial amounts of oxygen and dust. Oxygen requires multiple generations of stars to form. Stars must be born, burn through their fuel, and explode, scattering heavy elements before the next generation can use them. Webb found this entire process already well underway, when the universe had barely had time for one stellar generation. The models said it was too soon. Then in early 2026, that record fell. A galaxy designated MOME Z14 was confirmed at just 280 million years after the Big Bang, 10 million years earlier still. It was brighter, more compact, and more chemically enriched than anything current theory predicted for that era. Elevated nitrogen levels in its spectrum suggested massive stars had already lived and died inside it, seeding the galaxy with heavy elements before the universe was 3% of its current age. One researcher on the team said simply, "It looks nothing like what the models predicted. These are not isolated anomalies. They are accumulating into a pattern." Webb keeps finding galaxies that formed too early, grew too fast, became too mature for the timeline built from decades of prior observation. The implication is not that the Big Bang is wrong. It is that the earliest chapter of cosmic history, the period when the first stars ignited and the first galaxies assembled, happened faster and more violently than anyone had calculated. The universe was more productive in its infancy than anyone expected. Webb's records will almost certainly fall again. The team behind MOME Z14 noted they had examined only a small fraction of the sky. Older, brighter, more surprising galaxies almost certainly exist in regions no telescope has yet observed. Every new piece of sky Webb looks at could hold the next record breaker. What makes the early galaxy problem particularly interesting is not just that these galaxies exist, it is what they imply about the rate at which the universe did its first work. Current models of galaxy formation suggest that dark matter halos form, first collecting ordinary matter into gravitational wells, and that gas then cools and collapses inside those halos to form stars over timescales of hundreds of millions of years. The galaxies Webb is finding suggests something much more efficient was happening in the early universe. Star formation rates far higher than the models predict happening in much less time than the framework allows. Some theorists have proposed that the initial mass function of early stars, the distribution of stellar sizes when the universe was young, may have been weighted toward much more massive stars than we see forming today. Massive stars burn fast and die young, fusing elements quickly and seeding their surroundings with metals faster than smaller stars would. Others have proposed that the early universe had conditions, higher gas densities, lower metallicity, different cooling rates that allowed much more efficient conversion of gas to stars than occurs today. The debate is active, the data is incoming, and the models are under revision. The deeper implication is this: we have been building our understanding of the universe based on observations of the universe as it is now, or as it was in the relatively recent past. Webb is showing us the universe as it was when it was barely beginning, and what it was doing then does not straightforwardly follow from what we know about what it does now. The early universe was not just a smaller, younger version of the current one, it was doing something different, faster, more violent, more productive. And the full story of how the ordered structure of today emerged from that early chaos is still being written. And yet, even with Webb pushing the limits, 90% of the estimated 2 trillion galaxies in the observable universe remain beyond detection. Their light has technically arrived, they are within the boundary, but expansion has stretched and dimmed it past anything current instruments can register. Now why 46 billion? The universe is 13.8 billion years old. The math says the observable radius should be 13.8 billion light years. Instead, it is 46. That gap is not an error. It is what happens when space itself doesn't follow the rules of ordinary distance. But before leaving the topic of light and time, there is one more dimension worth naming: the redshift. When an object is moving away from you, the light it emits is stretched. Each wavelength arrives slightly longer than it left. This is the Doppler effect, the same principle that makes a siren sound lower as an ambulance passes. In the expanding universe, galaxies are not moving through space so much as being carried by it, but the effect on their light is the same. The light from distant galaxies is stretched to longer wavelengths as it travels through the expanding space between them and us. Galaxies close to us have small redshifts. Galaxies from the early universe have enormous redshifts. Their light has been stretched so dramatically by billions of years of expansion that what originally left as ultraviolet radiation arrives as infrared, invisible to human eyes. This is how distances are measured in the early universe. The redshift value of a galaxy directly encodes how long its light has been traveling, and therefore how far away the source was when it emitted the light, and how far away it now is given the expansion that has occurred since. JWST 140 had a redshift of 14.3. MOME Z14 had a redshift of 14.4. Each incremental increase represents an earlier slice of cosmic time, a smaller fraction of the universe's current age. The cosmic microwave background, the oldest light detectable, has a redshift of roughly 1,100. Meaning its wavelengths have been stretched to over 1,000 times their original length since they were emitted 300 background and 80,000 years after the Big Bang. The 46 billion light-year radius feels like a violation of something fundamental. In a universe with fixed, stable space, it would be. But the observable universe does not exist in fixed, stable space. It exists in space that is growing continuously everywhere, in every direction between every pair of points, without a center and without a boundary. When astronomers say the universe is expanding, they don't mean galaxies are flying outward through space like debris from an explosion. they mean space itself is stretching. The fabric of the universe is adding more of itself. And that stretching applies everywhere, simultaneously between the Milky Way and Andromeda, between Andromeda and the next galaxy over, between every galaxy and every other galaxy in the observable universe, all at the same time. In an ordinary explosion, there is a center. Objects move through space and slow down over time. In the expanding universe, there is no center, no outward direction, no boundary that everything is rushing toward. Every galaxy is roughly stationary in its local region. Every galaxy is also receding from every other galaxy because the space between them is growing. If you lived in Andromeda and looked back at the Milky Way, you would see the Milky Way moving away from you, not because the Milky Way is running, because the space between you is expanding. Now apply this to a photon in transit. A photon released by a distant galaxy 13 billion years ago begins moving toward Earth at 300,000 kilometers per second. While that photon travels, the universe keeps expanding. The distance the photon still needs to cover keeps increasing, not because anything moved, but because space is being added between the photon and its destination. The photon never stops moving at the speed of light, but the finish line keeps receding. A photon from a galaxy far enough away would lose this race entirely. The space being added ahead of it exceeds what it can cover. That photon will never arrive. The photons that do arrive are the ones that won that race. And by the time they arrive, the galaxy that emitted them has been carried much further than the photon actually traveled. A photon that crossed 13.8 billion light-years during its journey arrives from a galaxy that now sits 46 billion light-years away, because expansion kept carrying that galaxy further while the light was in transit. 46 billion is not a paradox. It is the record of expansion accumulated over 13.8 billion years of travel time. This also creates something called the cosmic event horizon, the boundary beyond which light sent today will never reach us. It sits roughly 16 billion light-years away. Any galaxy currently beyond that line is sending light toward us right now that will never arrive. The expansion of space in front of those photons is growing faster than the photons can close the gap. And here is what makes this genuinely strange. 16 billion light-years is well within the observable universe. We can observe objects 46 billion light-years away, but we can only ever receive new signals from objects currently within 16 billion. Galaxies between 16 and 46 billion light-years are visible because their ancient light has already been traveling long enough. But any event occurring in those galaxies tonight will never be seen from Earth. The observable universe has two different horizons, a past horizon from which ancient light has already arrived, and a future horizon from which nothing new can ever reach us. The past horizon is 46 billion light-years. The future horizon is 16 billion, and the future horizon is shrinking. In 1998, two independent research teams studying distant supernovae, stellar explosions used as reliable distance markers, found something that contradicted every prediction. The universe was not slowing down under gravity. It was speeding up. The expansion rate was increasing. Something was pushing space apart with growing force, and no model had included it. No instrument had been built to look for it, and no one had imagined it was there. They named it dark energy. Not because they understood it, because the equations had a gap, and the gap needed a name. In 2011, the leaders of those two teams shared the Nobel Prize in Physics for the discovery. Dark energy currently makes up roughly 68% of the total energy content of the universe. It appears to be a property of space itself, an energy inherent to the vacuum that does not dilute as space expands. More space means more vacuum energy. More vacuum energy means more expansion force. The more the universe grows, the faster it grows. This is not a process that levels off. As far as current physics can determine, it continues indefinitely. There is a problem, though. When physicists try to calculate what the energy of the vacuum should be using quantum field theory, the most precise framework available, the number they get is roughly 10 to the power of 120 times larger than the value actually measured in cosmological observations. That is not a rounding error. That is the largest discrepancy between theory and measurement in all of physics. The prediction and the observation differ by 1, followed by 120 zeros. Some physicists have called it the worst prediction in the history of science. The vacuum energy is clearly there, dark energy is real, the expansion is accelerating, the measurements are solid. But why the vacuum energy has the value it has, why it is so extraordinarily smaller than quantum mechanics predicts it should be, remains completely unexplained. This is not a minor gap in understanding. It is a signal that something fundamental about how physics works at the intersection of gravity and quantum mechanics is either missing or wrong. The answer to that question, when it comes, will almost certainly require new physics, a framework that doesn't yet exist. 27% of the universe is dark matter, something with mass and gravitational pull that neither emits, reflects, nor absorbs any form of light. It cannot be photographed. It cannot be directly detected by any currently operating instrument. Its existence is inferred entirely from the effects it produces on things that can be seen. Galaxies rotating too fast for their visible mass to explain light, bending around galaxy clusters more strongly than visible matter accounts for, and the large-scale structure of the universe matching. Simulations only when dark matter is included. Remove dark matter from the models and the structures we observe should not exist. Despite decades of searching, no one has ever caught a dark matter particle in a detector. Experiments buried deep underground to shield them from cosmic ray background noise have been waiting for decades for a dark matter particle to collide with an atomic nucleus in their detectors. Nothing confirmed. The Large Hadron Collider at CERN has been smashing protons together at energies high enough to produce particles that theories predicted should be dark matter candidates. No detection. Multiple satellite observatories have been watching for gamma-ray signatures that would indicate dark matter particles annihilating each other in regions of high dark matter density, like the center of the Milky Way. No clear signal dark matter exists. The gravitational evidence is overwhelming and has been independently confirmed by many different methods, across many different scales. But whatever it actually is, whatever particles it is made of, whatever properties they have beyond mass, remains completely unknown. It is the most abundant form of matter in the observable universe, and humanity has not yet been able to detect a single particle of it in a laboratory. That leaves 5% for ordinary matter atoms, the stuff of chemistry, planets, stars, and gas. 5%. Everything ever photographed, every civilization that has ever existed, every instrument ever built, 5% of the universe's total content. But even that 5% has a story that begins not with the first galaxies, but with a fraction of a second so brief that the numbers required to describe it carry more zeros than there are stars in the observable universe. Before the observable universe had galaxies, before it had stars, before it had atoms of any kind, there was a period lasting less time than any physical process. Science can currently measure that left marks on everything that followed, not the Big Bang itself, something that happened just after it. In a window of time estimated at around 10 to the power of -35 seconds, written out a decimal point followed by 34 zeros and then a 1. The universe expanded by a factor so enormous that the region of space containing everything that would become the observable universe went from smaller than a single proton to roughly the size of a grapefruit. The name for this event is cosmic inflation. To put the scale in any human terms, imagine a single bacterium invisible to the unaided eye, inflating to a size larger than the Milky Way. That is roughly the ratio of size increase that inflation accomplished. And it happened in a duration so short that more of those instants fit inside a single second than there are seconds in the entire age of the universe, raised to several powers. Why does this matter? Because inflation solves problems that the Big Bang alone cannot. The first is the uniformity problem. Look at opposite ends of the sky points separated by 93 billion light years and measure the temperature of the ancient microwave radiation arriving from both directions. It is nearly identical. They differ by less than 100,000th of a degree. For two regions of space to have the same temperature, they need to have been in contact close enough to exchange heat and reach equilibrium. But those opposite ends of the sky are so far apart that under normal expansion, they could never have communicated in the entire history of the universe. The time hasn't been there. Inflation solves this because before it happened, the entire region that became the observable universe was smaller than a proton, small enough that every part of it was in contact, reaching thermal equilibrium, smoothing out differences. Then inflation stretched that tiny uniform region into something vast. The near-perfect uniformity existing across 93 billion light-years today is the preserved memory of a moment when everything that became those 93 billion light-years was packed smaller than an atom. The second problem inflation solves is the flatness problem. Measurements show that the observable universe is geometrically flat. Parallel lines stay parallel. The angles of any triangle add to exactly 180 degrees. Space doesn't curve on the largest scales. Maintaining that flatness over billions of years of expansion requires the initial density of the universe to have been calibrated with extraordinary precision. Any slight deviation would have either collapsed the universe under gravity long before stars could form, or allowed it to expand so rapidly that matter never had a chance to clump together. Inflation explains this by stretching any initial curvature into negligibility, just as the surface of Earth appears flat when you're standing on it, because the curvature of an entire planet is spread across the scale you're experiencing. But inflation did something else, something that makes it responsible not just for the size and uniformity of the observable universe, but for all of its structure. In the moment before inflation, the universe was so small that quantum mechanics governed it entirely. And quantum mechanics has a rule: perfect uniformity is physically impossible at small scales. Energy and density fluctuate randomly and continuously. There is no such thing as a perfectly smooth region of space at quantum scales. These fluctuations existed in the pre-inflationary universe, tiny random variations in density, incomprehensibly small, constantly appearing and disappearing. Inflation froze those fluctuations and stretched them to cosmic scale. A region fractionally denser than its neighbors by a quantum amount became, after inflation, a region fractionally denser than its neighbors by a measurable amount written into the large-scale distribution of matter across the observable universe. Those slight variations became the seeds of everything. Over hundreds of millions of years, gravity pulled on those overdensities. Denser regions accumulated more matter, less dense regions emptied. The subtle pattern amplified over billions of years into the dramatic architecture visible today. Every galaxy in the observable universe, including the Milky Way, including Andromeda, including every galaxy ever photographed, grew from a quantum fluctuation that existed during a period lasting 10 million trillion trillionth of a second. After inflation ended, the energy driving it converted into particles and radiation, the hot, dense plasma of the early universe. For the next 380,000 years, the universe was opaque. Photons could barely begin moving before colliding with the dense fog of charged particles surrounding them. The universe was sealed a brilliant, impenetrable medium through which no information could travel. There is a period between the end of that plasma phase and the formation of the first stars that astronomers call the cosmic dark ages. When the fog cleared, 380,000 years in the universe became transparent, but it was transparent to nothing. There was no light source anywhere. Hydrogen and helium gas filled the universe, cooling slowly, beginning to clump under gravity. For roughly 200 million years, the universe was dark. Not metaphorically, physically. No star had yet ignited. No galaxy had yet formed. The universe was opaque, then transparent, then dark, waiting. Then in the densest clumps of gas, gravity won. The first stars ignited. Those first stars, designated Population 3, stars a category that has never been directly observed, were almost certainly very different from the stars forming today. The gas available to them contained no heavy elements at all, only hydrogen, helium, and trace lithium. With no metals to help gas clouds cool and fragment, the first stars likely formed from much larger gas masses, producing stars potentially hundreds of times more massive than the Sunday. Those massive stars burned fast lifetimes of perhaps 1 million years compared to the Sun's 10 billion, and died violently, seeding the surrounding gas with the first heavy elements the universe had ever contained. No one has yet observed a Population 3 star. They formed too early and died too fast for any telescope to have captured them directly. But their signatures, the heavy elements they scattered, the patterns they left in the gas around them, the ionization they produced in the surrounding hydrogen, are being searched for in the spectra of the oldest galaxies Webb can reach. The first direct evidence of Population 3 star formation may be found within the next decade. Then 380,000 years and the temperature dropped to roughly 3,000 degrees, cool enough for electrons to combine with protons and form neutral hydrogen atoms for the first time. The moment neutral atoms formed, the charged particle fog disappeared. Light flooded outward in every direction simultaneously. That ancient flood of photons, the signature of the universe's first transparent moment, is still traveling. It has been cooling and stretching for 13.8 billion years. Today it exists as a faint microwave glow, filling the entire sky from every direction, cooled to just 2.7 degrees above absolute zero. This is the cosmic microwave background, and right now it is passing through the walls of every room, through the atmosphere, through the space around you, roughly 400 photons of it in every cubic centimeter of the universe, including the air in front of your face. In March of 2025, researchers using the Atacama Cosmology Telescope in Chile released the clearest images of the cosmic microwave background ever produced, 5 times the resolution of the previous best. For the first time, the images captured not just where matter was concentrated in the early universe, but how it was moving. The polarization of the ancient light revealed the actual currents of hydrogen and helium gas flowing through the infant universe, the streams that would hundreds of millions of years later collapse into the first stars. Having a map of where things were, and now for the first time also seeing where they were going, the cosmic microwave background is a hard wall. Behind it lies a period that emitted no light capable of reaching us because the universe was too dense to let light escape. No future telescope, regardless of power or design, can see before 380,000 years after the Big Bang using electromagnetic radiation. The limit is not technological. It is written into the physics of the early universe. What comes before that wall, the details of inflation, the first fraction of a second, can only be inferred. What formed after it is visible. And what that visible structure looks like at the largest possible scales is something no one anticipated before they actually mapped it. There is one more thing about inflation worth noting, not a technical detail, but a consequence that makes the whole story stranger. Inflation, according to most models, did not happen once and then stop. It happened here in the region that became the observable universe, and it also continued happening elsewhere. The same quantum fluctuations that were occurring before inflation began are also occurring at the boundary of any inflating region. Some of those fluctuations are large enough to trigger new episodes of inflation in adjacent regions, which then produce their own vast stretches of space, which then have their own quantum fluctuations, which trigger new inflations, indefinitely. This scenario, called eternal inflation, suggests that inflation never globally stops. It stops locally in patches, producing regions like the observable universe. But at the largest scales, inflation keeps generating new regions of space continuously, with each inflating region producing a vast volume, potentially with different initial conditions, different random seeds for structure formation, possibly, even different values of fundamental constants. The observable universe, in this picture, is not just one small part of a larger universe. It is one small part of a larger structure that is still actively producing more universes. This is one of the most speculative, but also most carefully reasoned areas of modern cosmology. Eternal inflation follows from the same inflationary models that explain the uniformity and flatness of the observable universe models that match the cosmic microwave background data with remarkable precision. The same physics that makes the observable universe make sense also implies something far larger and stranger beyond it. Whether that implication reflects physical reality or is a feature of the mathematics that doesn't map onto anything real is a question that current science cannot answer, because by definition, other inflationary regions are causally disconnected from ours. Their light will never arrive. When astronomers began mapping the large-scale distribution of galaxies in the 1980s, they expected something roughly uniform. Galaxies distributed more or less randomly across space, with local clusters and voids, but no dramatic overarching pattern. What the surveys actually revealed looked like the internal structure of a sponge, a vast network of intersecting filaments and sheets surrounding enormous hollow spaces containing almost nothing at all. This structure is called the cosmic web. It is the largest organized feature in the observable universe. It spans the entire 93 billion light-year diameter, and it is the direct product of those quantum fluctuations from the inflationary period amplified by gravity over billions of years into structures visible across half the observable universe. The cosmic web has four components. Nodes are the densest intersections where filaments converge and galaxy clusters accumulate. Some clusters contain thousands of galaxies gravitationally bound together, moving as a collective through space. The Perseus cluster, one of the nearest massive clusters to the Milky Way, contains over 1,000 galaxies within a region roughly 10 million light-years across. The Perseus cluster is so massive that the hot gas trapped between its galaxies, gas heated to tens of millions of degrees by the cluster's gravitational energy, pours more energy into space in X-rays alone than all the starlight, from all the cluster's galaxies combined. In 2022, astronomers using the Chandra X-ray Observatory mapped pressure waves moving through that superheated gas in Perseus, acoustic waves set off by the supermassive black hole at the cluster's center rippling through the cluster over timescales of millions of distant years. Those waves were translated into a sound frequency by researchers shifted far outside the human hearing range into something audible, and what they produced was a deep, resonant hum, the deepest note ever detected in the universe, 57 octaves below middle C on a piano. A sound the Perseus cluster has been producing for billions of years in a medium no human instrument could have heard, in a space no human will ever travel to. Filaments are the long threads connecting nodes made of dark matter, hot gas, and scattered galaxies. They stretch for hundreds of millions of light years. The largest confirmed filament, designated Quipu after the knotted rope system of the Inca, extends roughly 1.3 billion light years. A single continuous thread of dark matter and gas, longer than the distance from the Milky Way to the most distant object visible to the naked eye, multiplied many hundreds of times over. Along these filaments, matter flows slowly toward the nodes, funneled by gravity, across billions of years. Walls are the flat, sheet-like structures where filaments merge, chains of galaxy clusters spread across surfaces spanning 500 million light-years or more. The Sloan Great Wall, mapped in 2003 stretches, roughly 1.4 billion light-years, and contains multiple superclusters. The Hercules Corona Borealis Great Wall, identified in 2014, may span up to 10 billion light-years, so large that its existence challenges current models of how quickly structure can form. Some cosmologists debate whether it is a single coherent structure or a statistical artifact. It remains one of the most contested objects in modern cosmology. And voids are the spaces in between, roughly spherical, between 100 and 300 million light-years in diameter, where the density of matter is a small fraction of the cosmic average. The Bootes void, discovered in 1981, spans roughly 330 million light-years and contains only 60 known galaxies. Under average cosmic density conditions, a region that size should hold thousands. The matter that belongs there has been drained away, pulled along filaments toward nearby nodes over billions of years. The void keeps emptying. Every year, more of its remaining matter flows out. The distribution of these components produces something counterintuitive. Voids dominate the volume. Roughly 80% of the observable universe by volume is occupied by these near-empty spaces. But filaments and walls, despite occupying far less volume, contain more than 50% of all matter. The universe is not evenly filled. It is threaded, concentrated along the edges of vast hollow bubbles, with most of its volume almost empty. Our own location sits on the outer edge of a supercluster called Laniakea, mapped in 2014 for the first time by measuring galaxy velocities and mapping their gravitational flows. Laniakea spans over 500 million light-years and contains more than 100,000 galaxies, with the Milky Way near the edge of one of its tendrils. The name comes from Hawaiian, meaning immeasurable heaven. The Milky Way is not at the center of Laniakea. It is not even close to the center. It sits on the periphery, in a relatively quiet region, far from the most active nodes. Laniakea itself sits within a larger structure called the Pisces-Cetus supercluster complex, a filamentary structure roughly 1 billion light-years long, one of the largest confirmed structures in the observable universe. And that complex connects to other complexes. The pattern extends in every direction for the full accessible breadth of the observable universe. Every location in the observable universe is embedded in this structure. No galaxy sits in truly empty space. Every galaxy is either in a filament at a node or on the edge of a void, and the voids themselves are surrounded by the filaments and walls that define their boundaries. The total number of galaxy clusters in the observable universe is estimated at around 10 million. The number of individual galaxies is 2 trillion. The number of stars is 10 to the power of 24. The number of planets is likely higher. Still, estimates suggest roughly 1 trillion planets in the Milky Way alone. And if that figure holds across the observable universe, the total number of planets exceeds any label human language has a compact word for. Most of those planets almost certainly do not harbor anything complex. The conditions for complex chemistry stable stars, the right distance for liquid water, the right mix of elements, long geological stability, are not guaranteed by any mechanism, and current observations suggest that even habitable conditions may be rare. But rare applied to 2 trillion galaxies, each containing hundreds of billions of stars. With trillions of planets, each still produces a number that strains credulity in the other direction. The observable universe contains enough locations, enough stars, enough planets, and enough chemistry that rarity and abundance stop being simple concepts. But the galaxies are not the skeleton. They are tracers, bright markers identifying the locations of dark matter concentrations that cannot be directly seen. The actual framework of the cosmic web, the filaments and halos within which galaxies formed and reside, is made of dark matter. The visible universe is a thin, luminous coating on an invisible structure. Strip away the dark matter scaffolding, and the cosmic web dissolves and the galaxies within it scatter. Between the galaxies and filaments, the space is not empty. It is filled with the intergalactic medium gas, heated to millions of degrees by the energy of structure formation, so diffuse that it is essentially transparent to visible light. This gas is extremely difficult to observe directly, but it accounts for a substantial fraction of all ordinary matter in the observable universe. More ordinary matter exists in the diffuse intergalactic medium than in all the stars and galaxies combined. When astronomers try to account for all the ordinary matter in the universe, the 5%, a significant fraction of it keeps being missing from their counts of stars and galaxies. The intergalactic medium is where most of it actually is. The cosmic web is still evolving. Filaments continue funneling matter toward nodes. Voids continue emptying. Clusters at the densest nodes are growing through mergers, collisions between entire galaxy clusters playing out over billions of years. The Bullet cluster, roughly 3.7 billion light-years away, shows 2 clusters that collided roughly 150 million years ago, passing through each other. The collision was so energetic that the hot gas in each cluster, the ordinary matter, was slowed by the impact and left behind, while the dark matter in each cluster, which doesn't interact electromagnetically, passed right through without slowing. The Bullet cluster became one of the strongest pieces of evidence for the existence of dark matter, a direct visual separation between where the mass is and where the light is showing they do not coincide. And the cosmic web is slowly coming apart. Dark energy is accelerating the expansion of space faster than gravity can maintain the long-range connections between distant clusters. The clusters at individual nodes are bound tightly enough to remain intact, but the filaments between clusters are being stretched. The connections are thinning. Tens of billions of years from now, galaxy clusters will become isolated islands in an expanding void, no longer connected to each other by any structure. The cosmic web will dissolve. Consider what that means in terms of what has already been built. Over the last 13.8 billion years, the universe has taken quantum noise, random microscopic variations, and converted them through gravity and time into the largest organized structure that exists. Filaments stretching 1 billion light-years, clusters containing thousands of galaxies, a web spanning the entire observable universe. It took the full current age of the universe to build this. And now dark energy, the dominant force in the universe by a wide margin, is working against it. The cosmic web is the universe's greatest structural achievement. It is also temporary. The timescales involved make temporary a strange word. The cosmic web will dissolve over tens to hundreds of billions of years. Stars will continue to form for trillions. The last red dwarf star, the smallest and dimmest kind, will exhaust its fuel in roughly 10 to 100 trillion years. After that, the universe's stellar era ends. What follows is an era of cooling remnants, white dwarfs slowly radiating away their stored heat over timescales of quadrillions of years. Neutron stars spinning down black holes, gradually evaporating through a quantum process called Hawking. Radiation over timescales that dwarf the current age of the universe by factors that make the current age negligible. The universe we observe right now, with its active star formation, its cosmic web still partially intact, its galaxies visible in every direction, is the universe near the peak of its complexity. The peak has not yet passed, but looking at the physics it can be seen approaching. Everything that exists now, the web, the galaxies, the stars, is a brief, luminous episode in a much longer story of cooling, dimming, and dispersal. But the cosmic web is only what can be seen. The observable universe, with all its structure, represents at most 3% of what exists. The remaining 97% is beyond the horizon, unreachable. And the question of what lies there is one of the few in all of science that no observation can currently answer. The edge of the observable universe is not a wall. There is nothing there, no boundary marker, no change in the density of space, no difference in the operation of physical law. The limit exists only from this vantage point. From Earth, at this moment in cosmic history, this is simply as far as any light has had time to reach us. Step outside the boundary, and all you would find is more universe with its own horizon, extending 46 billion light-years in every direction. The question of what lies beyond cannot be answered by observation. By definition, light from beyond the horizon has not reached us. No signal has arrived. No measurement is possible. Everything known about the region beyond the observable universe comes entirely from theory, from taking the physics that operate within the observable portion and asking what they imply about the vast region outside it. The most conservative estimate based on the statistical geometry of the observable universe places the total universe at least 250 times larger than the observable portion. That implies a total diameter in the range of 23 trillion light-years, a region so large that the entire observable universe, with its 93 billion light-year span, would be a small province within, but 250 times may be a drastic underestimate. Cosmic inflation, if it proceeded as most models suggest, expanded the pre-inflationary region by such an enormous factor that the observable universe is essentially negligible in comparison. The mathematics of inflation predict that the region which became the observable universe was just one small, smooth patch within something vastly incomprehensibly larger. Some models predict the total universe is at least 10 to the power of 23 times larger than the observable portion, a number that exceeds the count of all stars in the observable universe raised to powers beyond comfortable expression. In those models, the observable universe is not a significant fraction of the total. It is a rounding error. What lies beyond the horizon almost certainly looks like more of what we already observe. More galaxy clusters, more filaments and voids, more structure shaped by the same dark matter scaffolding, the same dark energy, the same fundamental forces. The physics that operate within the observable universe give no indication of stopping or changing. The universe appears homogeneous and isotropic on the largest accessible scales, the same in all directions, the same at all observable locations. The most straightforward conclusion is that it continues in the same fashion without boundary. And if the total universe is large enough, which current models strongly suggest, then probability makes a strange demand. Every physically possible arrangement of matter will occur somewhere. Not because of any mystical principle, but because probability applied to a large enough volume becomes a certainty. Given enough coin flips, every sequence eventually appears. Given enough space, every arrangement that physics permits eventually occurs. Somewhere beyond the observable horizon, almost certainly there are regions statistically similar to our own, similar galaxy distributions, similar stellar systems, similar conditions, not identical, but similar in the way that two different cities built from the same materials and following the same engineering principles can end up resembling each other without ever being designed to do so. There is no scientific consensus on whether this implication is meaningful or merely a mathematical curiosity. But the physics that produce it are not speculative. They are the straightforward extension of what the instruments actually measure. Now the observable universe is also shrinking in a meaningful sense. Right now, the observable universe is technically growing every year. More light arrives from regions previously beyond our reach. But dark energy is simultaneously accelerating expansion. The future event horizon, the boundary beyond which new signals can never arrive, sits at 16 billion light-years. Galaxies between 16 and 46 billion light-years are visible because their ancient light has already been traveling long enough. But new events in those galaxies, new signals sent from them tonight, will never reach us. And if the total universe is large enough, which current models strongly suggest, then probability makes a strange demand. Every physically possible arrangement of matter will occur somewhere, not because of any mystical principle, but because probability applied to a large enough volume becomes a certainty. Given enough coin flips, every sequence eventually appears. Given enough space, every arrangement that physics permits eventually occurs. Somewhere beyond the observable horizon, almost certainly, there are regions statistically similar to our own, similar galaxy distributions, similar stellar systems, similar conditions. The distance to the nearest statistical repeat of the observable universe under standard assumptions would be roughly 10 to the power of 10, to the power of 122 meters, a number so large it cannot be meaningfully expressed in any unit. But in an infinite universe, distance is not the same as absence. There is a related question the observable universe raises that is worth naming directly. Is the universe infinite? Current measurements of the geometry of the observable universe suggest it is flat to within about 1% precision. A flat universe can extend infinitely, without boundary or edge. If the universe is flat and infinite, it contains infinite space and infinite repetitions of every physically possible configuration. This is not science fiction, it is the straightforward implication of flat geometry applied to an infinite extent, which is what the measurements currently suggest is most likely. But most likely is not the same as certain. The universe could be slightly curved in either direction at scales larger than the observable portion, slightly positively curved, making it finite like the surface of a sphere, or negatively curved in ways the current measurements can't detect. The data does not yet decisively answer the question. The universe may be infinite. It may be very large and finite. Current instruments cannot distinguish between them. There is also the Hubble tension, a persistent disagreement between two different methods of measuring how fast the universe is expanding. Measurements based on the cosmic microwave background produce one value. Direct measurements using nearby supernovae and other distance markers produce a slightly higher value. The gap is small in absolute terms, but statistically significant enough that it cannot easily be dismissed as measurement error. Both methods have been checked and rechecked. Both continue to produce their respective values with increasing confidence. The disagreement suggests either that one measurement method has a systematic error no one has yet identified, or that something about the early universe or the late universe doesn't fit the current model in a way that hasn't been accounted for. Some physicists have suggested it could point to new physics, a form of dark energy that changes over time, or an additional component to the universe's history that no model currently includes. The Hubble tension is one of the most active and unresolved debates in cosmology today. Over the next roughly 150 billion years, galaxies outside the gravitationally bound local group will recede past the point of any possible detection, not destroyed, not moved, just carried by expansion until their light falls below any physical threshold of observation. The last galaxy beyond the local group will not disappear in a dramatic event. It will fade slower each year, dimmer each decade, redshifted to wavelengths no instrument can reach, until it simply is no longer there to see. A civilization arising in the far future would inherit a universe appearing to consist of a small, isolated cluster of galaxies surrounded by an apparently empty void. The cosmic microwave background would have been stretched to wavelengths so long that detecting it would require instruments of planetary scale. The evidence for the Big Bang would be undetectable. The evidence for the cosmic web would be gone. The 2 trillion galaxies filling the current sky would have been permanently carried beyond any observation. That future civilization could study everything available to them and conclude with all the rigor of science that the universe contains, only a few dozen galaxies has always been like this and shows no evidence of ever having been otherwise. They would be looking at the same universe we inhabit, and they would be completely wrong and unable to know it. The universe we are living in right now is in some ways the universe at its most observable. The window is open. The evidence is here for inflation, for the cosmic web, for the microwave background, for the expansion and its history. Every key piece of information about the origin and structure of the universe is currently accessible. That window is slowly closing, and it will not reopen. The observable universe, 46 billion light-years in radius, 2 trillion galaxies assembled from quantum fluctuations, stretched by inflation, and shaped by dark matter and dark energy across 13.8 billion years, is built almost entirely from things that have never been directly detected. Dark energy at 68%, dark matter at 27%, 95% of everything invisible, understood only through the gaps they leave in what can be measured. The entire history of astronomy, cosmology, and physics, every instrument ever built, every discovery ever published, has been conducted from within the 5%. That remaining 5% is ordinary matter atoms, the stuff of chemistry, biology, planets, and stars. Of that 5%, the majority is not in stars or galaxies. It is diffuse gas stretched across the intergalactic medium, too thin to form stars, too hot to cool, spread through the filaments of the cosmic web at temperatures of millions of degrees. For decades, astronomers counted up all the ordinary matter they could find in stars and galaxies and came up short. The missing matter was eventually found in this hot, diffuse intergalactic gas, detected in X-rays and ultraviolet, essentially transparent to ordinary light, present everywhere in the web and almost impossible to observe directly. Stars, all the stars, in all 2 trillion galaxies, account for roughly 0.5% of the universe's total energy content. 0.5% of everything that exists is burning nuclear fuel, fusing lighter elements into heavier ones, pouring light into surrounding space. Every stellar nursery ever photographed, every supernova ever recorded, every star visible to the naked eye on any clear night, 0.5%. But what that 0.5% does is extraordinary. Stars are not just lights, they are factories. In the cores of stars, pressures and temperatures high enough to push atoms together, despite their mutual repulsion, produce nuclear fusion, the conversion of lighter elements into heavier ones. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, nitrogen, neon, magnesium, and further up the periodic table. In the most massive stars, this process continues up to iron, the heaviest element fusion can produce, without consuming more energy than it releases. When those massive stars exhaust their fuel, they collapse under their own gravity and rebound in a supernova explosion, briefly outshining their entire host galaxy, scattering the elements built in their cores across hundreds of light-years of surrounding space. But supernovae are not the only way the universe builds its chemistry. When 2 neutron stars spiral together and merge events so energetic that they were predicted to be detectable as gravitational wave sources, the collision produces a kilonova, a flash of light that creates conditions even more extreme than a supernova core. Kilonovae are responsible for producing many of the heaviest elements in the periodic table: gold, platinum, uranium, and others that Iron Peak supernovae cannot generate efficiently. In 2017, the LIGO and Virgo gravitational wave detectors picked up the signal of 2 neutron stars, merging approximately 130 million light-years away, the first gravitational wave event to also be observed in light. Astronomers watched the kilonova unfold across multiple wavelengths over days. The amount of gold estimated to have been produced in that single event was roughly 10 times the mass of Earth. Every piece of gold on Earth, in every ring, in every circuit board, in every vault, came from events like that one in stars that died before the solar system existed. The iron in blood was made in a stellar core. The calcium in bone was made in a stellar core. The gold in any piece of jewelry anywhere on Earth was made in a neutron star collision. The oxygen in every breath was made in a stellar core. These elements did not exist at the Big Bang. The universe at the beginning contained only hydrogen, helium, and trace amounts of lithium. Everything else was built inside stellar processes, in explosions and collisions and mergers that occurred across billions of years in stars no one will ever see that died billions of years before the Earth formed. The observable universe is structured so that the components most relevant to complexity, stars, rocky planets, liquid water, organic molecules, are by any cosmic measure negligible. 5% of the total with stars, a fraction of that 5%, rocky planets, a small fraction of those stellar systems, and complex chemistry rarer still. And yet the instruments produced by that chemistry have measured the temperature of the cosmic microwave background to 100,000ths of a degree, have detected gravitational waves from the merger of two black holes, a billion light-years away, ripples in the fabric of space-time, smaller than 1/10,000th of a proton's diameter, detected by mirrors 4 kilometers apart, have resolved individual galaxies forming 280 million years after the Big Bang, have mapped the distribution of matter across billions of light-years, and inferred the invisible scaffolding holding it together. The scale of the observable universe, 93 billion light-years across 2 trillion galaxies, mostly dark, mostly empty, mostly composed of things that cannot be seen, can feel like an argument for smallness, for irrelevance. But consider what the numbers actually show. The universe is 13.8 billion years old. For the first, roughly 380,000 years of that time, no light could travel freely. For the following 200 million years or so, the cosmic dark ages, no stars yet existed. The universe was hydrogen and helium gas cooling and slowly clumping under gravity, with no light source of any kind. Then the first stars ignited. Then the first galaxies assembled. Then, over billions of years, those galaxies produced later generations of stars, enriched with heavier elements from the deaths of earlier ones. Then around the stars of those later generations, planetary systems formed. Then on at least one planet with the right conditions, chemistry organized itself over billions of years into self-replicating structures. Then those structures evolved eventually into organisms capable of asking questions about the universe they found themselves in. That entire arc, from hot plasma to organisms capable of asking cosmological questions, took 13.8 billion years. And the questions those organisms have asked, using instruments built from the same atoms forged in stellar cores, have produced measurements accurate enough to determine that the observable universe is 93 billion. Light-years across, contains 2 trillion galaxies, is expanding at an accelerating rate driven by something that makes up 68% of everything and has never been directly detected, and began from a region smaller than a proton, in a moment of expansion so fast that the physics required to describe it does not yet fully exist. The observable universe does not require a telescope to enter. The cosmic microwave background, 400 photons per cubic centimeter everywhere, at all times, is passing through you right now. It has been passing through every point in space since 380,000 years after the Big Bang. It carries the imprint of quantum fluctuations from the inflationary period, the pattern that became the cosmic web, that became the 2 trillion galaxies, that became the stars that built the elements, that built the instruments, that detected dolaries. That is what the observable universe is. Not a distant concept, not an abstraction, a continuously unfolding record of everything that has happened, still arriving from every direction at the speed of light. The window is open. The evidence is here. It will not always be.